Force, Energy and Power, number 17. Now before we go any further, this question, I'm going to do it here, is a classic example of why subscripts are a really good thing. I'm going to cheat by having quite a lot of them written in ahead of time. Because if we read the question number 17, we're told that we've got a car of mass 1,200 kilograms towing a caravan of mass 1,000 kilograms. So I've got MC for car, 1,200, MV for caravan, 1,000, and MT for total, 2,200. We're also told in the question the acceleration is 2 meters per second squared. We're told the force of friction, so F, R, C, R for friction, C for car, 500 newtons. But the force of friction on the caravan, FRV, 200 newtons, which means the total force of friction, FRT, is 700 newtons. Make up your own jokes at this point. I'm not childish enough to do it. And so, we're asked in part A, calculate the force exerted by the engine of the car. So I'm going to put FE for engine equals F_un for unbalanced force, the force that's causing this whole collection of vehicle here to accelerate at 2 meters per second squared, plus the total force of friction, which conveniently we've already worked out by accident. So the force from the engine must be the total mass times the acceleration plus the force of friction. Doing a bit of algebra here just to show that we can still do it after all these years. That will be 2,200 kilograms times 2 meters per second squared plus 700 newtons for the friction, which means the force from the engine must be 5,100 newtons. There we go. And that's part A done. In part B it says, what force does the tow bar exert on the caravan? So we're going to use the same kind of logic that we used in number 16. We want the force on the tow bar. That's going to be equal to the unbalanced force, but only the unbalanced force on the caravan, plus the force of friction, but only the force of friction on the caravan. So the force on the tow bar is going to be 1,000 kilograms for the mass of the caravan, times the acceleration of 2 meters per second squared, plus the force of friction on the caravan, which was only 200, and that is going to give you a grand total of 2,200 newtons. Now, part C is asking us, if the car is travelling at a constant speed of 10 meters per second, excellent, that gives me a huge clue. Assuming the frictional force is to be unchanged, calculate 1, the new engine force, and 2, the force exerted by the tow bar on the caravan. So, C part 1 is really easy. It's a constant speed. That means that the acceleration is 0 meters per second squared. At which point, several of you are going to leap into the trap of saying, if there's no acceleration, there's no unbalanced force, so the force must be 0, and I'm going to go, you've forgotten about friction, haven't you? So it's going to be same logic as here, the force from the engine equals the unbalanced force plus the total force of friction. And indeed, you would be correct in saying the unbalanced force would be 0 because the acceleration is 0. But that doesn't mean the friction goes away. So the force from the engine when the car and caravan are travelling at a constant speed is 700 newtons. And then in C part 2, we're asked the force exerted by the tow bar on the caravan. And the logic follows the same way. Force on the tow bar would equal the unbalanced force, but only the part that's acting on the caravan, plus the force of friction, but only the part that's acting on the caravan. So Once again, you would be correct to say the unbalanced force acting on the caravan when the caravan is travelling at a constant speed and therefore not accelerating is indeed 0. But that doesn't mean that friction's gone away. So we've still got the 200 newtons of friction that was acting on the caravan, so the force on the tow bar is 200 newtons, like so. And then part D, the car brakes and decelerates at 5 meters per second squared. Calculate the force exerted by the brakes, assume the other frictional forces remain constant. So, let's have a think here. What do we need? The first thing we need to do is work out the force that the brakes produced in total. And that's going to be the mass times the acceleration. And the acceleration is going to be exactly what it told us in the question, 5. So that's going to be 2,200 kilograms times 5 equals 11,000 newtons, which is quite a lot of newtons. And then we need to apply some logic. What's creating this braking total force, this total braking force? It's going to be a combination of the force from the brakes plus, remember, the frictional forces always oppose the motion, so they'll have a braking effect as well. That's why we still had 700 newtons there and 200 newtons there, even though it was travelling at a constant speed. So that's going to be 11,000 equals the force from the brakes plus the friction forces, which means the force that's coming only from the brakes, not including the friction forces, is 10,300 newtons. And there we go.